Okay, we are recording. So for the very last time this semester. Okay. Now, so today it's all about the final. If I exhaust your questions on that and there's time after, then we can talk about homework too. I'm slowly but surely getting through grading what has been turned in so far. Expecting / hoping / dreading that more will be turned in later. So as a reminder, all coursework of any kind must be in by Thursday, December 12th, because grades have to be in on Monday the 16th, entered in SOAR in the morning so that you can see them by afternoon. And whatever's turned in by the 12th, I will at least have time to look at it. Why not? What? Okay, I mean, I'm used to the end of a semester being miserable during that time where you all are done with finals, so you're finished, and then I have those 3-4 days of continued suffering. Okay. Now the final has been written, so I will be giving the test on Thursday down at the coast. Someone, a grad student, obviously not in this class, will be, but who has previously taken the class, will administer it up here. Okay, so what I've done is, of course, the two parts problems. So there are 8 problems. Undergrads must do any 5 of your choosing. Grad students must do any 6. Okay. So there's some choice there. So they'll be modeled after the 8 problems that you see on the practice test. Now, if you feel like you have the time, if you go ahead and attempt more problems than necessary, so for example, if you're an undergrad and you attempt 7 problems, then I will grade all 7, and then I will take your best 5 as the ones to count towards that part. Okay, and then for the lightning round part, 25 questions total. Undergrads must do any 10. Graduate students must do any 13. Okay. What? Don't be mean to the grad students. They suffer enough as it is. Jeez. Okay. Besides, what if you were a grad student someday? Okay. All right. And then as far as the makeup of the final, okay, or of the lightning round in particular, questions taken from section 7.5 onward. So roughly evenly distributed. So that one section on interpolation, or mean interpolation, oscillatory, and then the rest coming from Chapter 9, differentiation integration. Chapter 10, root finding methods. Okay. Yes?
Unique solutions for lightning round like earlier.
What?
Unique solutions for lightning round.
Oh. I don't think I have time to make up all of those. I mean, for once I did for a midterm, I had solutions already written for those chapters. And well, yes,
So like the other tests, the lightning round questions will be pulled from concept check.
yes, they will. So that is what you should study. Yeah. As not like the questions will be carbon copy, but there will be like slight mutations of those questions. Okay. Okay. Other questions about, or general questions about the final. Like I said, we'll discuss the practice test momentarily, but other questions first. Yeah.
We haven't finished all the concept checks. We'll just finish those for you to at least grade them. Is that like another question?
Oh, I'm not sure what you're asking. Right.
If we haven't finished a lot of the concept checks, and
Oh, I
we
see.
still finish them so you can grade them and we can study them.
Oh, okay. So in other words, if you go ahead and like hurry up and get them in, okay. Well, there's 2 days, so time is short. But okay. I will do my very best. I've graded. Yeah, you may have seen I've graded some quizzes today. I will do my best to grade whatever quizzes are sent in before the final. Yeah. And at least you only have to attempt 40 to 50% of a lightning round question. So, for example, if you haven't gotten to any of the ones from chapter 10, but you feel good about the ones from chapter 9, you can complete the whole section based on those alone. So, okay. Okay. But yeah, the quizzes don't take too long to grade, so I'll make sure to at least get those out. Okay. Any other general questions? Oh. Okay. All right. Okay. Oh, okay, hold on. Let me turn up the volume. Okay, what's the question down there?
Camera is, I think it's on the audience view instead of the instructor.
Oh.
Yes, on the students. So.
Okay.
I think they have to change that down on their end, right?
Okay.
This classroom wasn't working.
Dr. Harris flipped it earlier.
Oh, okay.
It was shined to the front and he flipped it.
Oh.
You guys have to change that down there on the computer.
Who's your camera?
We can flip our camera, but we can't flip yours.
Okay. Let me see.
I don't know.
Oh, maybe.
This screen wasn't working earlier.
Okay. Okay, I'm not entirely sure how to work this. Okay, let's try this.
Oh.
Is that what?
Yeah.
Okay. All right. Good to know for future reference. Okay.
And then, you say if we complete up to 9, that's good enough for the test, for the final? Up to homework 9?
Let's see. Or wait. Oh, you mean homework 9?
Yeah, if we go up to homework 9, because I think
Oh.
up to homework 9.
Okay.
So,
well, yeah, because. Okay, because homework 10 only has the last 2 sections. That's going to be like maybe 4 or 5 questions out of 25. So.
I I need to get on 10 on it. So I want to do
No, what I mean is, if you haven't touched these yet, that's not really going to hurt you for the lightning round, because there'll still be enough questions from prior sections that you'll have seen. Okay. Yeah, because let's see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so there's 11 sections. So there's like 2 to 3 questions per section in the lightning round. So, and since you only have to answer 10, you basically pick your favorite 5 sections and focus on those if you want. But it's the same rule as for regular problems. I'll grade as many things as you write something down on, and and then pick your best.
What if we would do 8 problems? What if we do take 8 problems, but we don't do all the right? Would you give us partial from all 8?
No. Yeah. I mean, you'll get partial credit for anything you do, but what I'll do is I'll look at, like, if you try all 8 problems. Yes, this is what I mentioned earlier. I'll grade all 8, and then look at the points you get for all 8. Take the highest 5 in your case, because you're an undergrad, and that's your score for that part of a test.
So we couldn't get like 110, and then 10 would be extra.
Oh, you mean like you want it to be extra credit?
So what I'm saying, for example, suppose we get up to 110, would that 10 count to the entire grade?
Okay.
Say you want to C and you want to get to a B, and that will guarantee you a B.
Okay. Well, let's see. Actually, I guess it would be better to make it extra credit instead of best ones. Is that? Well.
I probably won't get to 110.
Okay.
Let's be honest. But anyway, and then what if 8 o'clock comes and we got like one more problem then? Like, because isn't it, do we get more time? Because it's like, I don't know if I really, but I do it all the
Wait,
time.
Okay.
Our test on Thursday is at 2:45.
What?
What?
No, hold on. Yes. Right?
No.
No, never mind. That's next Thursday.
Okay. No. This is during regular class time. Okay.
Sorry, guys.
Now here's something that I feel pretty strongly about. That apparently some of my colleagues may not feel the same way, but I don't like situations where due to everyone's class schedules, that some students in the class end up having significantly more time on a test than other students. Like, sometimes it happens where, okay, like in the middle of the day, a class has a test, and then the regular class period is ended, and several students have to leave because, like, they have another class, and then the professor decides, oh well, it's not, he doesn't mind giving whoever's there more time, which ends up giving the students who don't have class an unfair advantage, for example. So how this applies here is, I want to make it, what's important to me is that students up here in Hattiesburg and down at Gulf Park are allotted the same amount of time. So in other words, if I personally don't mind giving a reasonable amount of additional time past 8 o'clock, but I want to make sure that students in Hattiesburg can also do the same thing. So it's something when I actually don't know who specifically will be proctoring up here, although I can guess, but I'm supposed to give a test to Dr. Tian, and then she will task a grad student with proctoring up here. So I can, we can agree on something, like maybe staying till 8:15 or something like that. we're not going to make this a marathon. So because I always have the option of curving a test. So if there's a matter of the test being too long in general and then driving the scores low. So if there's a problem with length, I'd rather fix it that way. Well, saves everybody time. Okay. All right. Okay. So, well, as far as trying extra problems, like if you're required to do 5 or 6 or whatever, and you go beyond that. Okay, I'm willing to count those as after picking your like say your best 5 to be your base score. Then the ones that that were not your best, I'm still willing to consider as extra points. So because I know that I have a feeling that most people's homework averages might be pretty low. And homework counts for 30% of a grade. So I'll let you have this one chance to try to go above and beyond and pull your grade up higher. So, okay. So, but keep in mind, like if you're gonna attempt all of them, make sure that you do 5 of them well. So, like pick the ones that seem least threatening and do a lot on those, and then see what you have time for. You might find that the lightning round is a good way to rack up some extra. Okay. Other questions? And also we'll open up to questions about the practice final.
A question about the second question.
Okay, on Lagrange differentiation.
So when you did it, you used Taylor expansion. When I did it, I used equation 9-6, which is that
For the error. Okay.
the error.
Yeah. Let's see.
What page is the question on?
334.
Okay. Okay. Yeah. Actually, I'm not sure why I did it using Taylor in this case, because you could. Yeah. So what he's referring to, equation 9.6, is the error formula for coming from Lagrange interpolation, where it really basically comes from a Lagrange error. Yes, you can definitely use that. All right.
To add to that, because I wanted to ask that also.
Yeah.
In that formula, one of the explorations, 9.1.4,
Yeah.
asks us to give a general error formula.
Right.
So in that general error formula, we already know h to the something.
Right.
So why can't we just use that and say, since the general formula is h to the n j plus k, and we can j is 1, k is 1, so h to is
Yeah.
the k is 2.
So I should point out that that is something that cannot be used every time. Like where that can be, from that problem 914, where that can be used is if your interpolation points, if you're using every single point from x minus jh to x plus kh, so at every integer multiple of h. Whereas this problem right here in the practice test uses x naught minus h, x naught, and x naught plus 2h. In other words, it skips x naught plus h.
What I did was try, instead of I'm thinking of how many points to the left of x naught,
Yeah.
many points to the right. So in that sense, we're still using 1 point to the
If all you want is the order of accuracy, the thing to be careful about in that case is that sometimes where this can be thrown off is if you're using like for example, the center difference. X naught uses x naught plus h, x naught minus h. Now you could treat it as a case where you're also using x naught, as the coefficient of x naught happens to be 0. So then you get the correct order of accuracy in that case. So it's just a matter of which points you use on either side, because it doesn't actually use x naught.
Yeah.
Let's see. Well, actually, in that case, it still will give a correct order of accuracy. All right. Actually, yeah, that would work in general. Yeah, that's how many points you.
That's a justified reason, because when I was doing the practice solution,
Yeah.
that was what I did. I had that to solution.
Yeah.
We had to do Taylor expansion, which is kind of long.
Oh yeah, yeah. Yeah. Well, so in something like that, I would want you to give at least a brief justification of what I did. Yeah. So yeah, because otherwise someone could just guess. Oh. Okay. Yes, I am. That's a very important question to ask.
I still don't understand how we get the asymptotic error constant.
Okay. Which problem are you looking at?
8, 7, and 8 both have to asymptotic error constants.
Okay, so it's number 8?
Yeah.
Okay, so the way this works so this question is about fixed point iteration. All right, I'll be prepared for questions about any of them. Okay, well, first a comment that was made about number 2. Don't need to use Taylor expansion to get order of accuracy. Can use equation 9.6. Okay. All right. Now, so for number 8, fixed point iteration. From Taylor expansion, so what we have here is x. So I need to make this a little bigger. Okay. X k plus 1 minus x star, which is equal to g of x k minus g of x star. Okay, and by Taylor expansion, that'd be g prime of x star, x k minus x star. Now, so this is what happens in the most general case when its derivative is non-zero. That means linear convergence, where this is the so g prime, or absolute value of g prime, is the asymptotic error constant. I'm going to put absolute values around everything. All right. Now, but if we continue, okay. All right, so that's squared. Let's see. All right, if I go one more term, okay. So G triple prime over 3 factorial, and then this cubed. Okay, and so on. This continues.
Sorry. So, what are we Taylor expanding? G of x k around x. Like this Taylor expansion, how did we get Taylor expansion?
Okay. Well, really, what you're doing is you're expanding G of xk
Around x.
around x star, and that's where all of this comes from. Because really, if I took this minus G of x star, moved it to the other side, that is a Taylor expansion of this. So what happens is, most cases, this derivative right here is non-zero. So this is a term of interest. This is a leading error term. So we say, oh, it's the previous error to the first power, therefore linear convergence, and that's the error constant. But suppose that this is 0, which is what happens in problem 8. The first derivative at the root is 0, therefore this is a leading error term. So we get G double prime over 2. Quadratic convergence in that case. But suppose that this derivative and this derivative are 0. This is a leading error term now. So this would be cubically convergent, and so the asymptotic error constant is always going to be some derivative of g at x star over the corresponding factorial, assuming that all prior derivatives at x star are 0. And don't forget absolute value. Asymptotic error constant must be non-negative. Okay, so if GR of x star is the first non-zero derivative, and this is r greater than or equal to 1, at x star, convergence is of order r. And that non-zero derivative over the factorial is the asymptotic error constant. Okay. All right. So problem 8 highlights an unusual case that fixed point iteration converges more rapidly than in general. Yes.
A little bit more on 8. In the solution, you say since g prime of x star is equal to g1 is equal to 0, is g1 equal to 0 in the given equation?
Oh, no, it's not.
That's what I was thinking.
Yeah. Okay. Yeah. So only g prime of x star is 0. G of 1 is equal to 1.
Right.
Yeah, because it's a fixed point. So yes, that is a mistake. Okay. So okay. Whoops. Okay. All right. Other questions about this one?
One more thing about this, since it's really short and it's easier than most. Do we have to do the Taylor expansion, or is that kind of what you were just explaining there before? Because it seemed like once you got the solution, you really just took the first and second derivatives and then just said it converges quadratically.
What I did was I looked to see how many derivatives were non-zero,
Right. Okay.
or how many were zero before I hit a non-zero one.
Right. So you couldn't find the third derivative, therefore.
Well, there was no need to,
Okay.
because the idea is okay. First derivative, it's zero. Okay, so that bumps up the quadratic.
Right.
Second derivative, non-zero, and that's why I make a note of that there in the discussion. That g double prime of 1 is equal to 2. If that had been 0 also, then I must go to the third derivative term and inspect it. So really the legwork you do on a problem like this is examining the derivatives until you hit a non-zero one.
So we don't need to do Taylor expansion.
So it
Um,
basically we get a constant value.
I'm sorry.
So we more of need a constant instead of, because like the second derivative is not constant, which is 2, which is quadratic.
Oh, well, okay, that's just because of this particular function. But so, but the thing is, we don't even care if it's a constant, if a derivative is a constant, because all we're doing is we're taking each derivative and plugging in the fixed point and seeing if it's non-zero at that point. So if everybody's situated, well, actually, in this case, because of it's being a quadratic, its second derivative would have been non-zero anyway. Yeah, but so that's something that's like incidental to this example. If I give something like maybe something involving an exponential or whatever, wherever derivatives are more interesting, then generally what you would need to do is, you have a fixed point, and you got to substitute that in to derivatives. Keep taking derivatives and substituting in until you get something that's non-zero at the fixed point. Okay.
What I'm asking is, since we're just looking at the derivative.
Yeah, you do not need to write out the Taylor expansion.
Okay.
Yeah. I mean, you'd have the information to do it anyway, but yeah.
So just go straight to find the first and the second derivative, basically.
Yeah. However many you need.
So whichever one don't give a 0, don't equal to 0. That's where we know to stop.
Once you get a derivative that is non-zero, yes, that's the stopping point. So so in this case, the second derivative was non-zero. Everything prior to that was 0. So then we know, okay, it's quadratic.
How the function you give us is a quadratic.
I actually don't recall what function I put on here, but it's probably not.
Okay, number 7.
Okay, so our name of questions number 8 before we move to number 7. Okay, number 7.
So, in the solution you gave, you said the error appears to be reduced by a factor of approximately 1/2,
Mhm.
which implies linear convergence with. So, are we supposed to include the asymptotic error constants when we're asking questions like this?
The way this problem is worded, no. You would not be required to supply the constant. So really what is required here is it converging quadratically? If not, why not? And in this case, it's because of the double root, which causes f prime to be 0 at the root. We require f prime to be non-zero at the root to have quadratic convergence. Okay. So, asymptotic error constant not required unless asked for. So generally, Newton's method in general, convergence is quadratic with the asymptotic error constant equal to f double prime at the root divided by 2f prime at the root. And the thing is, if the root is a double root, then c is undefined. So that right there would tell you it's not quadratic in that case. So so generally speaking, if a derivative at the root is non-zero, Newton's method will converge quadratically. Now, whether you actually get that depends on whether your initial guess is good enough, but that's a separate matter. But yeah, so what needs to be done in this problem, besides actually grinding out the iterations, since you're given the exact value of a root, so then you need that to get the errors, so that you can see how the errors are behaving. Remember, when it's quadratic convergence, the number of correct decimal places roughly doubles from one iteration to the next. And that definitely did not happen here. Now, how you would detect linear convergence is like in this problem like this, you go ahead and compute a few iterates, you compute a few errors, and you find that there's roughly the same ratio of errors. Like in this problem, it's 1/2. It might be a different ratio. Maybe the error is being reduced by a factor of 4 every time. But the point is, it's a consistent ratio. That's linear convergence. Okay. Other questions about number 7?
Not specified in it.
Okay.
We are finding the asymptotic error constant and we need the root. Well, generally say we don't know the root, we're trying to approximate. So if we had not known the root, would it be possible to find the asymptotic error constant?
Yeah. So okay. So, yeah, you would need the root. To actually get a value for the asymptotic error constant. Yeah, because all of these asymptotic error constants depend on the root.
So in the problem we're trying to solve, for instance, we don't know the root.
Okay, so in other words, if it's not given,
Yeah.
then yeah, you wouldn't be able to. Yeah, so I would not ask that, unless it's something where it's converges so rapidly that you compute a few iterates, say it's Newton's method, and you may not have that value to many decimal places, but you can see, it's converging to 2. You can tell in that case. The only exception would be bisection, just because the constant's always a half. But yeah, I will not ask you to compute something that's impossible. Seriously. Okay. Even though it might feel that way.
Also, most of we have a specified number of digits, so that means we just use 7.
Okay. Using 7 here was a personal choice. If I don't specify, then I don't care.
Well, okay.
Yeah. If you want a guideline, say like 4 decimal places or something.
Well, for the boss product.
Okay. So that one.
So we're transforming from one interval to the other.
Yeah. Since the nodes and weights for Gauss quadrature are specified with quite a few decimal places, looks like 10.
10, yeah.
which I suppose right away makes us a candidate for a problem to skip. So-
And I hope it's 3 nodes, not 5, like in the textbook.
Sorry, what? Oh.
Yeah, in the textbook, the example you worked was a 5 node problem, and it was 5.
Oh, and I don't remember exactly what. Well, I'm not gonna have you do a 5-node problem on a test, but yeah. Okay. Maybe what I should do in that case. Well, actually, like for instance, in this example here, the weights are repeating decimals. So those could be expressed as fractions. Although the same cannot be said for the nodes. So, okay. I will be fine with reducing the number of decimal places that you use. So in other words, you don't have to use if you want to do the Gauss quadrature one because you're not liking the other ones. Then, like for instance, you want to use like 5 decimal places throughout the computation. That's fine because it'll still produce an answer that's similar to what I'll get from my key. So I'll be able to tell if you're doing it right. Okay, so that was problem 4. Okay. All right. Yeah, but generally when I'm grading these things, I'm going to go with any reasonable interpretation of what was actually written, because I mean, obviously that's all you have to go on. So if there's something that I was silent about, like how many decimal places, I'm not going to take off points saying you didn't use enough decimal places. So. Okay. So are we working our way through his test backwards, or?
But do we have to, for number 4, can we skip all of this that we write out for the definite integral, all of that, with the formula and stuff, and just go straight to complete consequence 1?
Okay, some of what I put in the. Okay, I definitely do not expect you to write things out the same way I did in the solution, because the solution is not, like, for example, if I was actually taking this test, I would not write it out like this. Because the way I've written the solution is also to try to aid in your understanding of what was done. So, okay, so for problem 4, for evaluating the integral, so all I would expect you to carry out is taking the nodes and weights that you get from a formula sheet and carrying out the transformation. So like xi and wi. So let me write this down here. Only need to work out the xi and wi for nodes and weights on the given interval AB. So actually carrying out the transformation, not deriving it as I did there. And then once you have the nodes and weights, the final step, actually using the nodes and weights in that quadrature rule. So plugging in the nodes into the integrand, multiplying by the weights, and adding up.
So I noticed in the formula sheet you gave us, you didn't give us change of variable. Have I expect to memorize that.
Oh, okay. Okay. So that's something that is actually easier to memorize than one might think. So since the nodes and weights are given for the interval -1 to 1, need to scale the nodes and weights by b minus a over 2. Because all you're doing is, because the interval -1 to 1 is an interval of width 2. So you divide by the width of that interval, multiplied by the width of your interval, and then shift only the nodes by the midpoint, a plus b over 2. So that's it. So I'm hoping at 400, 500 level math students can remember that. Yes?
I did see on number 4 on the actual practice exam, not the solution, on the possibly useful, you did put the nodes and weights on there. So is that going to be included?
Oh yeah, everything on the formula sheet. Yeah, I really literally copied that into the real test.
Okay, perfect.
Okay. All right. Other questions about? I guess we're jumping around now. I don't care. Still have a good amount of time.
Is there a shorter way to do number 3?
Is there a what?
A shorter way.
Oh, okay.
I mean, it's not difficult, but yes.
Right. Yeah. So really, the most tedious part of this is the trapezoidal rule. So filling in the first column of your Romberg table. Now, if you're looking for a time saver, I can give you that. This is actually something I brought up when I covered this topic in the first place. Okay. So, when filling first column... Oh. The Romberg problem, 3. Okay. 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 Need these values of f. So, okay. So, first row, you're using a most basic trapezoidal rule. So you need f of a, f of b. And row 2, okay, the same values as well as f of a plus b over 2. So there's a lot of reuse of function values. So what you might want to do is, since you know from a specification in the problem how many times you'll have to use a trapezoidal rule, you can make a what you might want to do is like make a list, like a chart of function values. So like x values in one column and f of x values in the other. So row 3. So you need everything from above. So f of, okay. All right, so f of, all right, so instead of, so it's the midpoint of a and a plus b over 2. So 3a plus b over 2. And, okay. And then the other is the midpoint of b and a plus b over 2. So that's going to be a plus 3b. Oh, wait, this is over 4. All right. Now, I would not expect you to know these. The point is, you start with your endpoints, midpoint of those, and then midpoints in between these 3. Then you have 5 points, and if you needed to go again, which would make a long problem, you would take the midpoints of those. So you keep taking midpoints to get the new x values that you need from one step to the next. And if you, whoops. Stop that stupid thing. Okay. So recommend, what is going on here? Oh. Okay. Thanks. Making table of xi, f of xi, values, just so you keep track of what you need. Because there's also a formula in the text. It's not on a formula sheet, unfortunately, but if you want to take the time to learn it, it can be a time saver. Okay. So every time you apply the trapezoidal rule, composite trapezoidal rule, when you double the number of points, so what you have really is this. The new value for the trapezoidal rule is equal to 1/2 times the value up above in the Romberg table. And then you add up the function values at the all the points in between, the new points you're adding, and then you're multiplying by the h value for that application. So this is another way to more quickly go from one trapezoidal rule to the next. Now, okay. The other thing I want to point out is, notice how the extrapolation is done. It's always new value is equal to the more accurate value. So in other words, the one that's lower in a Romberg table, plus the difference of values over the appropriate denominator. And those denominators are always powers of 4 minus 1. So in your second column, the denominator is 3. Third column, the denominator is 15. So 4 squared minus 1. If there's another column, it would be 63. So 4 cubed minus 1. And so on. Yeah, there's definitely a lot more that I wrote in here than what you would need to write.
How you say the 3 come about?
I'm sorry, what?
How you say you get the 3 at denominator?
Oh, okay. So I'll make a note of these. So so denominators always a power of 4 minus 1. So 3. Okay. 3 equals 4 to the first minus 1. 15 equals 4 squared minus 1. And then 63 is 4 cubed minus 1. Okay. Yeah. Okay, what I mentioned before that. Okay. All right, so okay. All right, so right here in words is what you do for extrapolation.
On the formula sheet though, you kind of slightly changed the denominator.
Okay. I don't hold on. Oh, okay. Um, all right, so in this case, this is a more general Richardson extrapolation. This is the one you're referring to, right?
Yeah.
Okay.
I
Okay.
understand it. Just
Yeah.
you're explaining unfortunately.
Yeah, so this is more general than composite trapezoidal rule for Romberg, which, if you take into account that composite trapezoidal is second order accurate, and then the approximations that it generates by extrapolation are always the next even orders of accuracy. So what happens is, since first time around p would be 2, so you would still get 3 as the denominator. Then the next would be fourth order accurate, so that's so you get 2 to the fourth minus 1 and so forth. Yeah.
Yeah. One question number 6.
Number 6. Okay. All right.
So surely g of x has a fixed point in the interval 1.
Yeah.
So you said g of x has a fixed point if it's a contraction,
Yeah. So yes. So once you've established the existence of a fixed point, and that's where G is mapping an interval into itself, then yeah. So it's a contraction. Now, showing as a contraction deals with the like Lipschitz continuity, which is kind of hard to show directly. But yeah, so if you could show that the derivative is bounded by a constant less than 1, then yes, that would show it's a contraction.
The reason why I'm asking is, I think what I did was do g of x minus g of a minus g of b minus g of a,
Right.
of b minus a, and check which was less than 1.
Okay. Well, yes, that would also show that it's a contraction. I'm not sure if that's the easiest way to go, although that depends on the function.
So that would work.
Yes, that's valid. Yeah.
So we have to first show that the function is continuous and maps into itself first. Because I thought we could just do directly and show that this is less than this is constant and that's all.
Yeah, the condition on a derivative or the Lipschitz continuity, that by itself is not enough to guarantee contraction. So showing that it maps the interval into itself, that's part of it also. Yeah. So what? Okay, let me make some notes about that. Okay, so showing a unique fixed point. So first step. Okay, so and there'll be a situation where you're given an interval to work with. So first thing you do is find the max and min of your function g of x on the interval ab. So can use calc 1 ideas like the function given in a practice test does not have any critical points anywhere because it's a straightforward exponential function. So all you would have to do for this one is check the endpoints. Okay, so find the max and min of these of g by whatever means you prefer on the interval AB. Okay, and verify that these values are in AB. So that's how you can confirm that g of x maps the interval AB into itself. Because certainly the max and min are, but anything else will be too. So that's the first thing. That guarantees existence of a fixed point. And then the second thing is check check that the derivative satisfies this kind of condition on AB. So that's kind of similar. Need the max min of G prime on AB, because once you have that, that would certainly tell you whether this applies. Okay. Okay. And okay, or as based on the previous question. Okay. So that's all you need to do. Now, I'm not going to require you to get into the discussion of whether G is continuous. I mean, all the functions that we deal with in these kind of classes, exponential functions, polynomials, trig functions, etc., except possibly for some asymptotes or whatever, are continuous. So you can just jump straight to these two things. Show existence this way, show uniqueness this way. All right, what else you got? We had 20-something minutes.
So in that,
Good.
in that same problem 6, you say the G2 is equal to F. It's right there in the second bullet point, and it's at 1.6 or 87. Well, how do we get an F, an equal F right there?
Oh, well, because all right, so after determining that g of x is increasing, just because the derivative is seen to be always positive, so right off the bat, so you know from that the maximum of a derivative has to occur at the right endpoint of your interval, so at x equals 2. Okay, so all right, so then what I'm doing is I'm plugging x equals 2 back into the original function.
Okay.
Yeah.
So, I got it. That makes sense.
Okay. There's a question here.
So for number 5, you calculated the number of iterations by testing like the width of the interval. I did that by using theorem 10.2.2 and just said I needed 2 to the k where k was 4 iterations.
Oh yeah, you can certainly do that to figure out in advance how many iterations you're going to need.
Just making sure that's okay.
Yeah. So yeah, I mean you got to compute the iterates anyway, but I guess you can always use that to bound your suffering before you begin. Okay. All right. Okay, so number 5. Okay. All right. It looks like we've talked about. Oh, we talked a little bit about every question except number 1.
I was just about to ask, it's been a while since we divided different percentages.
Right. Okay. Yeah. So for Hermite interpolation, you're given 3 x values in this problem. So list them each twice. List y values twice, and then I pull up a divide difference table here. Okay, so your free x values. Okay, yeah, so twice, 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 and then when you go to the first column, this one right here, where you actually have to compute divided differences, what's going to happen is starting from the top one and every other one got to fill in derivative value because that's where, like in this case, the x values are equal. So that's where you need derivative. Then every other divided difference from this point on will be an actual divided difference, a quotient. But is there something in particular you had a question about?
Really, it's just been a while. So I knew how to get the first 3 rows, but then once I got to the second one, I kind of got confused on the.
Oh, right here?
Yeah, right there is where I started kind of losing track of what I needed to do to get those numbers.
Okay, yeah, yeah. So derivative, and then this one, it's y value minus y value divided by x value minus x value. So those are the ones that are immediately to the left of it. So that minus that, and because in this case the x values you're subtracting are distinct, so you can do that. But then you move down here, and the x values are the same again, so you must use a derivative. So your free derivative values of 1, 0, minus 1 will go in the first, third, and fifth spots in the table. The other ones, it's y minus y divided by x minus x. And then when you move to the next column, you won't have any more 0 over 0 situations. But like for this value right here, it's going to be, you look at the two values next to it, and you subtract those. And what I suggest, I know some people had difficulty digesting this when I was covering it in class, but like if these are your two y values, if you go diagonally down to here, and then to the left. So go diagonally down to your f values, your y values, and then to the left. This is the x value you subtract, and then here, this y value, you go up the diagonal to the y values, and that's the other one you subtract. So this divided difference right here is this minus this divided by this x value minus this one. So you keep using x values that are further apart. Then I move down to this one. It's the two neighboring y values are subtracted, divided by, and then I go down here to the left, that minus that. So here I go up and diagonally to the left. And it's these two x values that are subtracted, and so on. When I get to this column, it's like this one right here uses this x value and this one.
But which, sorry, can you say that one more time?
Okay, so like this divide difference right here, these y values,
Okay.
and then to get the x values, diagonal left,
Okay.
and then diagonal up and left. Yes, you are. In fact, yeah, that's what I was saying when I covered it back then. Make the, or I think I called it a cone. Triangle. Does that work? Okay. Okay. Not sure why I called it a cone because it's a 2D thing, but okay. All right. Yeah, and finally, when you get to the very last value, it'll always be the very last and very first x values because that's all you got.
But you go all the way back to that column.
Yeah, all the way to the, yes, every time. Yeah, you're always using the y values that are right next to it, and then going all the way back here for the x values. Because everything in between is a divided difference.
Right. Oh, that makes sense.
Okay. Because if you look at the definition, yeah, it's always divided differences over x values. Okay.
So I guess then the next part of it, actually finding
A polynomial. Yeah.
Would we fall down the top side?
You can use either one. You just have to be careful about what your linear factors are. So what I recommend is, so starting from this divided difference in this column, those are your coefficients, and you go down the top row, and then like the first term, that's just a constant by itself. The next one, you'll have x minus this value, and then this value. That's my one thing I keep doing with these examples. I keep refer to the index when I should refer to the x value. Okay, so third one, it's going to be this coefficient times x plus 1 and then x plus 1 again. Now some of these ended up being 0, so that's why we didn't have them. But so what will happen is you'll have linear factors x minus all of these except the last one. So this one right here is the odd one out. Because here we have, with repetitions, you have 6 points. Therefore, your final polynomial is going to be of degree 5. And notice that, look at the last term here. You have minus 3, and you have x plus 1 squared from these two, x minus 0 squared from these two, and then x minus 1 only once from that. And you can definitely leave it in this form. Do not multiply it out. It's a waste of time and harder for me to grade. And yeah, I mean, this is equivalent to using the bottom row where you start here. Like, it would also be 4 minus x plus minus x minus 1 minus 4 times x minus 1 squared, and going up this way. So they're very equivalent. I suppose if one row, either the top or the bottom row, one of them has more zeros, you can save yourself some work. All right, we still have 12 minutes for other questions about any problem. At least they're not MATLAB problems. Okay. 9.5.4. Okay.
Just above it, you think about why composites that solid conditions for integrating periodic function.
Right.
I thought sine is a periodic function.
So what?
I thought this is a periodic function.
Well, yes.
So because in the note you said when integrating periodic functions, the error is exponential order, or the h to the 2k. That what we want to do.
Well, yeah, so really 954 is about letting you see what happens with the error. Like, it's an attempt to try to demonstrate more rapid convergence than expected. So in other words, like, yes. So what would happen? Like, because normally when you use a composite trapezoidal rule, let's say if you use two values of n, like n equal 10 and n equal 20, and certainly you can use a, like, earlier in an assignment, or previous homework, you had to write a function that does a composite trapezoidal rule. You can certainly use that, and you can see the so what you can do is check the error for two different values of n. Now, normally for a composite trapezoidal rule, if you double the number of points, the error should be reduced by a factor of roughly 4. So the question is, does that happen in this case?
Well, I thought it should be better than that.
Yeah.
In this case.
Oh, was it not?
It wasn't.
Really?
So I don't know what the k in that formula stands for.
Oh, well, k can be any integer.
No, in the notes.
Oh.
H to the 2k.
Oh, that comes from the Euler-Maclaurin expansion here. So, where k is or 2k is the number of continuous derivatives. Of course, with sine k pi x to be infinitely many. So, well, how did the error behave?
It was still like normal trapezoidal.
Interesting. That kind of surprises me.
So I was thinking I made some errors somewhere Tried.
That's worth examining.
I've tried working with that house and
Oh my God. Well, how many points were you using?
I was doubling, so I doubled from when I used the code, I used from 2 up to 1024.
Okay, interesting. I wonder if I have that function here.
Yes.
Oh. Were you getting a value like this?
Yeah.
Okay.
But if you go to 100,
Sine 2 pi is 0. It will integrate sine 2 pi is 0.
Yes. The exact value is 0.
Yeah. So I was even surprised that it was giving us a value that's not 0. This is not exactly.
Well, no, but it's pretty dang small. It's smaller than machine precision.
Yeah, the error you're getting there is not from that; it's from machine.
Yeah. So now, as by contrast, I'm going to use the same function. Okay, Simpson's rule is pretty dang accurate, also. So maybe that was not such a good example, but okay. But Simpson's rule does not have the property of necessarily being exponentially convergent. This may not have been the most interesting example. Like a more interesting example would be a function that is a linear combination of like several like sines and cosines. So basically a Fourier series, but a truncated one. So it would still be periodic on the interval in question. Um, so okay, but yeah, it's, the symmetry in the trapezoidal rule, because like in quasi-trapezoidal rule, you have f of a and f of b, and then you have all the interior points that have a weight of 2. But when it's periodic and f of a and f of b are equal, then it also has a weight of 2. And so the symmetry that you get from these trig functions, these 2-pi periodic functions, leads to very nice cancellation of errors. And it's not the same as like normally in trapezoidal rule, you get a cancellation of the leading order error terms. What happens here is cancels all of them. So for periodic functions, it's incredibly accurate. Yeah, in any case. Yeah. Or someone yeah.
I got this problem that I realized it's not the same thing. In concept check 10 point for over 10.3, for problem 1 and problem 4, it's kind of actually the same question.
Oh wait, which section?
It's 10.3, concept check number 1 and number 3.
Okay.
It's number 1 and number 4. It said you try to make the fixed continuation for finding a solution of the equation, right? X minus dx. But then the next one is x equals 0, which would be all like the same thing.
Oh, okay. So if they're not asking exactly the same thing. So the first problem is really about the algorithm, whereas in question 4, since fixed point iteration is not designed for this problem, set up for x equals g of x, how can you change this problem that's given to you of this form to a problem of this form?
So I need to change the f of x equals 0 to x equals gx.
Yeah, so in that case, give an example of what g of x could be in terms of f of x. And so this is mentioned in the text, but also in my notes from class on this section, like what it so basically you're looking at equivalent equations, but you want to get from one form to the other.
So how do I get from fx0 to g to x equals gx?
Yeah. So
Oh,
yeah.
I know. I know now.
Okay, good.
9.7. I'm 9.7
Oh, this one. Okay.
I've managed to get x2. I've not figured out this order, but I noticed x2 was the square root,
Okay.
so it was plus or minus.
Mm-hmm.
But when I checked the table with zeros, observed your x2 was negative.
Right.
So, but when I solved mine, I used the positive value.
Oh well. What will happen is, so in that case, x1 would be yeah.
So it doesn't matter.
It doesn't because we're talking about a set of nodes and corresponding weights. So you just happen to index differently. Yeah. Because so you end up with a choice to take a square root, and our choice works out in the end.
Yeah, an easy way to solve all the
No, definitely not. And that's why I would not dream of giving this problem for n greater than 2. And maybe it can be done, but it's awful. Okay. Well, it's 8 o'clock, and also my battery's running low on my laptop, I just noticed. So, actually, I think it's symbolic of all of our batteries. If anyone has any additional questions, I'll stick around for a bit, but I won't keep everybody else here.